Good morning, everyone. So today we are here for the ninth session of the Responsible Artificial Intelligence course and the last one in the series. And today we have with us Anibha Athalye. She's the head of the practice department of the AI and practice department at the Persistent Systems. A key charter for her team includes partnering with customers, enterprises on their AI and ML initiatives and ensuring that their AI ML investments are converted into tangible business benefits. Hence, focus on ML in production beyond just ML, model development is a key area of interest and work for her. So we are very happy to have you here, Anibha, today for the session. And over to you.
Thank you, Prachi. I hope I'm audible.
Yes, we can.
So a very good morning, everybody, and thank you, Prachi, for the introduction. I am sure you've enjoyed all the sessions so far that have been conducted. What I'll be doing today is focusing on a topic called as reproducible AI. This forms the part of one of the ML operationalization work that we do, which is like once you have developed the model, happy with the first draft of model, kind of evaluated it across evaluation metrics, and then kind of take that and deploy it into environments beyond just the development. That's where the entire ML operationalization, which is how do you do automated deployment, how do you kind of do multiple variants of the model into production, how do you monitor it, how do you trigger the retraining pipelines, all of those come into picture. And reproducibility forms one of the core aspects of when you are trying to reproduce a machine learning model. And we'll kind of touch base on some of the core aspects. I'm going to be only focusing on reproducibility at experiment tracking and analysis level as part of this session, and happy to take on any further questions if there are. So let's get started. And what I have for you in the agenda today are a few slides which kind of talk about the reproducibility, how we are doing it in industry, and then I have a demo for you on one of the tools which allows you to do reproducible AI using experimentation analysis and tracking. So at the very essence of it, if I have to start with the basic of reproduction or anything that is reproducible, it means that anything which is the ability to kind of, be able to be copied, be able to be recreated such that, you achieve the similar outcomes as the baseline is what is reproduction or reproducibility enablement. Now, if you look at the very core of, any experiment that you conduct as part of your science course, you would start with a typical hypothesis that you have, of course, with the background that you want to start on. And then, you would be having certain input data. If I just take a very simple example of the experimentation that we used to do in chemistry, it all includes, what are the different chemicals, what are the different proportions of those chemicals that you are taking in as an input. You define the state of the chemical, solid state, liquid state, whatever it is, and then you follow a series of steps or a series of methods to kind of achieve or get to the results that you want to analyze or interpret. Now, when you're doing this experimentation, what also becomes important are the parameters which are getting passed to the experiment, which is like, what is the pressure, what is the, atmospheric temperature, and so on and so forth. Okay. And at the end of it, once you follow the series of steps, you kind of get to the results or the data. And you further then, analyze a series of results that have been achieved using that experiment. You interpret it to finally result a conclusion or something that you would like to kind of put under a publication. Now that publication that you do needs to document all the experiments, all the iterations that you have conducted, which has led you to those results to the T. And then that paper is what is kind of published, if I have to speak purely from a research angle or research activity kind of angle. Now, lot of time, the research scientists, as in the other research scientists of the community, would want to actually develop something on top of this baseline project or the baseline work that has been done. And that is where this, iteration or reuse actually comes into picture. Whilst they do that, all of us know that there is always a struggle in terms of being able to even reproduce the baseline results that have been called out or documented into the publication. And while the publication is being kind of reviewed, also there are a whole lot of questions in terms of the findings, reproduction, the method that is used, how do you know what are all the methods that were used, what steps were really followed before reaching that, and so on and so forth. And finding answers to this is not really easy, because getting the same results by following the methods or the steps that are mentioned in the documents are really not that easy. Now, a simple answer to this question as to how do I get the same results that are published in the paper is follow the paper to the T, and that is what all of us do. In spite of that, a lot of times, the outcomes or the conclusions that you get are significantly different than what was published in the original paper. And this is where we land more often than what we would like to believe. There is a lot of manual hacks that go into kind of reproducing a specific publication to achieve the outcomes. There is some or the other missing information, and I believe that the major cause of that is because when you're doing an experiment, you're kind of focusing into that, and then there's a slightly asynchronous activity of documenting or scribbling the inputs at the point where you really achieve the outcomes that you want to achieve in that specific experiment, and then further asynchronous activity of actually then converting those notes or the scripts that you copied while doing the experiment into a proper documented work. So what we are introducing over here when we are doing this process is two things. One is it is not happening hand in hand. While the experiment is happening, can the documentation of those happen? And the second is, of course, human dependency, while taking the notes, while converting those scripts or notes into a proper documentation. So net, what I wanted to kind of call out is that this is very similar to the experimentation that happens when we develop a machine learning model. And it is so in research, it is so in industry also, when we try to find out the best machine learning algorithms that can solve the problems that we are trying to find an answer to. So, you all must be very familiar with this. When you start with a machine learning hypothesis, you collect and analyze the data, you apply various techniques to kind of, get process that data, cleanse that data, get it to a state where you can fit a machine learning algorithm on top of that. You can iterate to various machine learning algorithms that are available to choose the best one that can give you the outcomes, go through the tuning part of it, and then you kind of present those outcomes to a business validator to say that, hey, is this good, is this bad, is there something else that I need to kind of do to get a better outcome, and then this process is iterative. Most of the times there are at least, if not 20 to 30 iterations that happen over this to get to the first draft of model that is presentable, that is something that can be shared with the business users. And all the when you're iterating, it's not always that if you're stopping at the 30th iteration, the 30th iteration is the best. Probably something which is the 27th iteration could be a best candidate that you would want to move forward. So net machine learning experimentation needs a lot of tracking, it needs a lot of documentation, and all this should happen without a lot of human efforts, without a lot of uh, uh, efforts going into kind of tracking this manually, which is what is happening right now. So my talk today really focuses on how is it being done, what are the toolings that are available from a perspective of being able to capture and track a lot of this experimentation that is happening, and how does that tracking and analysis actually help us to further take the machine learning models into deployment when we are trying to deploy it across various environments. Now, all of you, I don't know if you've been reading, but there's a lot of activity that is happening on the research aspects, wherein the research in ML traditionally was always non-deterministic, in the sense you don't put it under a specific paradigm of time. You don't necessarily follow all the paradigms of programming that are done in computer science, which is the continuous integration, the continuous delivery. Uh, not really, but there's a lot of activity that is happening, especially if you've read the program for reproducibility that was done by Neural Information Processing System. They've come up with a reproducibility checklist, which kind of goes with every publication. It's very detailed. It's like a guideline which kind of tells you how do you call out all the dependencies that you've used during your experimentation, your repository that you're kind of talking about, which is attached to a publication or a research paper. Does it have training scripts? Does it have evaluation scripts which can be reused for reproduction? Does it call out very specifically all the pre-training weights that have been called out? And more importantly, does it document all the results or the outcome to the T in terms of even graphical visualizations and all? It's a very detailed guideline, not specifically targeted at doing how you should be doing it, but necessarily what all should your publication really or a research paper really include to ensure that the reproduction of that is at a higher or at least closer to what the original conclusions you have drawn in your paper. And this has certainly achieved a significant amount of improvement on the reproducibility. So I believe that this is one of the good steps towards ensuring that you are drawing a parallel from a research angle that happens in ML to establishing those programming paradigms which have always been there from a normal in the other fields of computer science. And whilst machine learning is so much part of a computer science study, it is very important that all these steps also be kind of followed. Now, moving on from the research aspects, where you are kind of targeted towards using certain sample input data, you are targeted towards proving certain outcomes on top of that, or observing the data, observing certain experiments on top of that, and then concluding the results of top on top of it. We'll move to the industry part of it, wherein beyond the basic model development also there are a lot of activities and a lot of tasks that need to be done. So when we look at, typically building a complete AI machine learning enabled application, you're looking at three major players that play a role in building this. The first part, which is on the left hand side, is a data scientist persona, very similar to what we spoke from the research perspective also, wherein you are kind of doing the typical activity of taking in the data, analyzing in data, doing data pre-processing, feature engineering, anything and everything that is required to ensure that you are getting a good model outcome. And the model outcome has to be aligned, of course, to the goal that you have in mind. And if you see what is highlighted in blue over there, which is the experimentation tracking and analysis parts for, also forms part of the activities that a data scientist is expected to do. The second part, which is on the right hand side, is the DevOps engineer. And this is where the parallel in terms of the computer science fundamentals or the continuous integration, continuous delivery comes into picture. There's a third term that we define in machine learning, which is also called as continuous training, which needs to be enabled for those models which need to keep on learning at periodic intervals. So this is where we work on something that we called as automated model deployment. We work on rollout of new versions of the model, which we called as champion challenger rollout, which is like you have a model which is in production, and then you're trying to kind of iterate over it, optimize it, tune it, and you get a better version which you want to kind of test vis-a-vis your baseline models. And that's where the champion challenger rollout needs to be enabled on the system. You have other aspects like model monitoring, data drift monitoring, anomaly detections, retraining that you want to do. One of the other most important things over here is enabling auditing, which means that when you are going from the left to right of this, you have a basic draft model and you are kind of deploying it to any of the environments, higher environments, which is can be the staging environment, can be the testing environment, can be actually the production environment. There needs to be an audit. And what we mean by audit is we need to ensure that the version of the model that is deployed can be traced back to to all the model artifacts that are getting created. And this is where again reproducibility or traceability that is obtained by enabling reproduction really plays a key and an important role. And then in between both these left to right kind of a scenarios is the machine learning engineer, which is also enabling the data acquisition, which means that writing a lot of data pipelines, which itself can have a lot of mergerings, ensuring auto ML, which means that there are multiple algorithms that are working, and then of course peripheral activities like data labeling and annotation. So what I wanted to kind of call out on this slide is that beyond the basic model development that happens, there are a whole lot of activities that really need to be enabled from the point that the basic draft model or the first version or the baseline version of the model is developed to the time you actually put that model into production, and then kind of be able to do a continuous delivery or a continuous training of that model. Now, how does it typically happen when you say that I want to kind of enable deployment uh, of a machine learning model? Okay, and this is how traditionally is one of the ways that this happens. You have a user persona. This can be a data scientist who logs into typically a UI or an AI portal. This AI portal is enabled by the industry or the team that is working towards this model. You create your own workspace. This is very similar to how you would log in and create a workspace on any of the machine learning tools that you're using, and then you go ahead and you do a model registration. Now in a scenario where you have created the model offline, what you are doing is you are filling in a whole lot of information that is required for the system to understand to deploy this model. Just to take an example, this could be what is the Python version that was used to develop this model, what is the environment or the hardware on which this particular model was run, what is the algorithm that was used, what are the hyperparameters that have been used, all the details that are required, what is the version of the data that was used, all this is kind of supplied to the system. The system kind of reads through those details and creates the required artifacts. The artifacts would be actually the environment creation that is required for this model to be running, the git versions on which your source code is run. It will create all these artifacts, and then the deployment job NetNet selects these artifacts and the model becomes ready for consumption. So this is a typical deployment path where you are actually conducting an experiment or working on a machine learning model creation offline. When I say offline, what I'm trying to say is it is disconnected from your overall deployment workflow. You're doing it offline. You're doing it probably over your laptop, over a completely different system, which is net disconnected. Very similar to how you would do an experiment when you are kind of doing working even on a research problem if you are working in an isolated environment. Now let's kind of take this basic workflow and expand it to how experimentation helps with deployment. So you have the same set of steps. You have the user who's logging into the AI portal. You have the workspace. And what this workspace is then allowing you to do is actually run this experiment. So this blue box is something that comes into picture, and you are doing these experiments in the entire ecosystem, which is allowing you to do the deployments. Whilst you are running each of the experiments, and these boxes of various shapes actually indicate the variables that go into each of the experiment, the system has the capability of actually capturing all the changes that you are doing while you are running the experiments, which is what I kind of highlighted in my initial discussion, that there has to be a synchronous activity of the experimentation that you are doing and a capability of the system to basically log all the variables that you are kind of changing. So this capture of the experiment then results into artifacts which are actually created by the system itself, and then the deployment job kind of picks the best possible experiment outcome and then makes it ready for consumption. So this is what we are targeting. This is what is the best state for deployment, wherein the experimentation that is happening is actually working in conjunction with your end to end deployment. The system actually has the capability to capture all the variables that are going into your experimentation. Now what this enables is, this enables something called as traceability. So the model that is deployed for production, you can actually trace it back to the artifacts. You can actually trace back those artifacts to the experiment number, let's say to experiment number 2, which was done to get the best artifact or the best model for deployment. And when you go into the details of this experiment, you are actually able to capture all the parameters, right from the input data that was used, the validation sets that were used, the evaluation criteria that was used, to the hyperparameters that were used to train. And finally, yeah, automated artifact creation by the platform, which of course results into accelerated deployment instead of we manually going and creating each of the artifacts for the models that are happening. So that brings me to how do you really enable this? What are the changing parameters? What is it that I should be tracking when I say I am tracking all my experiments, so that I am able to kind of reproduce the work that I have done at any point in time. So let us take a very simple example, wherein we are saying that data is an input that is going to the system on the left hand side. And for this discussion, let us say that the data that is going at least is a constant, in the sense we are not really changing the input data itself at this point in time. And finally, what is coming out is the model or the outcome that is expected. Now, in between, what you are doing as a developer or as a data scientist is, of course, applying different types of pre-processing. You're doing certain feature engineering. You are doing algorithm selection and then hyperparameter tuning. Now, if you take any of these rows, you are really looking by n into n into n into n kind of a combination, which can result into the model that is desired. And any one of those ideally is the candidate which you would like to push forward. So being able to track all of these and some of the factors beyond this is what we say when we track reproducibility of a machine learning algorithm. So if I have to kind of bring all of this together, what really impacts reproducibility in ML? Your input data, of course. That is where you are trying to fit the model. So any changes to the input data is going to impact the reproducibility. The features that you're deriving on top of that, two actors working on the same input data can actually come up with two different features altogether, and that may impact even if you're using the same algorithm significantly. You have certain parameter tunings, of course the algorithm that you are selecting, the pre-processing methods, the software environment or the ML packages that you are trying to use and where you are trying to deploy, and then of course some of the non-deterministic stuff like random initializations that you have used in your source code, or the random data shufflers that you have used in your source code. So these are all the factors that are that impacts reproducibility in ML, and tracking each of these and being able to kind of then create a reproducibility path is what we are trying to achieve. uh, Before I get into the details of that, there are multiple types of reproducibility that is kind of called out. I would like to call out three of them that are typically discussed. The first one is the experiment reproducibility, which is what I have been talking about, which means that given certain input data and giving a certain method, you are looking at achieving the same kind of outcomes, or very similar or very close outcomes that have been published in the first baseline. So that's the experiment reproducibility, and that is what we will be focusing on largely as part of this discussion. The second type of reproducibility is the data reproducibility, wherein you are saying that the given some data, you can use actually alternative methods to get the same kind of outcomes. And the third is the method reproducibility, wherein you are saying that the method itself can change, the data itself can change, and then you are still able to achieve the same kind of outcomes. The discussion over here is largely focused on the experiment reproducibility. That's what we do as part of machine learning model developments in industry also. That is also largely an area which is also followed when we are trying to do research in machine learning. So with this, I'll take a pause. If there are any questions at this point in time, what I really want to do today is explain how this is done using some of the tools that are available. What you see on the screen are some of the AI and machine learning operationalization software which support experiment tracking and analysis as part of the overall operationalization features that they provide. These are by no way the complete set of tooling that is provided. There are a lot of other tools which provide that, but these are some that I've been using, provide some of the very good features as far as experiment tracking and analysis is concerned, or various versioning of the models is concerned. For the purpose of this demonstration, I'll be using MLflow, which is one of the open source tools. I'll take a pause for a moment if there are any questions at this point in time, or do we want to take the questions at the end? Okay, I'll move on. So, like I said, I'll be using MLflow to introduce to you the concept of how experimentation tracking and analysis is done. Uh, I'm not sure if all of you are familiar with MLflow, but MLflow is an open source platform which is used to manage machine learning lifecycle. This includes 4 key modules. The first module is MLflow tracking. This is the target, and this is where I'll be spending most of the time, which allows you to record your work or record your experiments and then further query those experiments at any point in time. It allows you to kind of record your code, record your incoming data, specific configurations, and then of course the results. The second module is MLflow projects, goes very hand in hand to actually address the reproducibility. It basically defines a structure or the way you should be packaging your machine learning experiments or machine learning work that you are doing, so that you are able to reproduce these runs on any of the other platforms. The third module is MLflow models. The MLflow models is allows you serving these models. So how do let's say I'm developing my model and I want to deploy it at SageMaker endpoint. All of it is kind of something that is covered by MLflow models. And finally, the model registry, which is also what something that we'll be seeing today, which allows you to really track or version various models. You annotate your models, and then it gives you a very nice single pane view of how many models across what environments these models are working. Might not be very pertinent or relevant from a research kind of angle, but from an industry perspective, since there are multiple models which are getting run, there are multiple versions of model deployed across environments like staging, testing, and production. This becomes a very, very important tool for us. So with that, I will directly jump into the demo. As part of this, this is all we will be covering. How do you, track the input data? How do you do features? How do you do the, environment, hyperparameters, and then, how do you track the non-deterministic outcomes? Uh, I hope my screen is still visible and all of you can see the MLflow screen.
Yes, yes,
So
we
this
can.
is great. So this is what MLflow looks like. Now let's go to a starting point where I am a data scientist, and what I'm trying to do is basically write a very simple Jupyter notebook for doing my experiments. And I've taken a very simple example over here. It's a decision tree working on lending club data site. I'm assuming that all of you are familiar with this data set. What this basically does is allows you to classify a loan as a good loan or a bad loan. Now, this is a data set that I'm using for my experiment, can be anything else. If you look at the notebook, it's very simple. What I'm trying to do is I'm trying to connect to my data source. Here it is Snowflake. Snowflake, those of you are not aware, is a cloud-based data warehouse, allows you to do data processing at scale in the cloud. So I have my entire data set in Snowflake, and this is a case in most work that we do in industry, wherein you wouldn't really be working on an offline data set like a CSV. Most times your data would be sitting in one or the other data lake or a data warehouse. It can be Snowflake, it can be Redshift, it can be any of the Hadoop systems from where you are kind of pulling the data on which you want to work on. So I have a live connection to this Snowflake. That is what I'm doing over here. Typical steps of looking at the data, doing certain pre-processing on top of that, doing certain feature engineering on top of that. And then what I'm trying to do at the end of it is basically do certain logging that I want to kind of keep a track on. So here at the end of the processing steps, if you see, I have actually captured my process data set as an as a CSV file. And this is something that I will use later on to store the data, which is the data that I have fed to my training algorithm. Once I do this, I go forward and then I start logging all my parameters with MLflow. So using MLflow is very easy. MLflow can be used as a remote or as a local setup. Now, if you see over here, I am using a completely remote setup. This is the server where my MLflow is running. It is not necessary, especially when you are doing a research at an individual level. It is not necessary for you to have MLflow running on a separate server. It can be running on your local server, in which case you can set the local host as your tracking UI. The next step that you see over here is where I am setting the experiment against which all these data should be captured. So I am defining an experiment called as loan predictions, which means that every time I run any of the experiments under this notebook, all of it will be captured under this experiment. MLflow allows you to create a new experiment altogether. So if an experiment is not existing, it will go and kind of create that for you and start logging. I'm doing my specific decision tree fitment over here, and here is where I start logging certain parameters. If you see, this is happening very synchronously. As you would be running this notebook, as you would be running the model, training the model, all of this will get logged. So the first thing that you see over here is called as logging of the matrices. So MLflow allows you to log various matrices. This is where you are able to document what is the metrics, what is the evaluation mechanism that I have used to evaluate my outcome. It allows you to log such something called as a parameter. In this case, because we are using decision tree, I am just logging one parameter, which is the depth of the decision tree that I will be inputting as an external parameter. It allows you to set something called as tags. Tagging is a very helpful activity which helps you pass on certain information that you have used while you have been creating the model to a reviewer, to a peer, or to somebody who is going to act as part of the overall ecosystem. For example, in case of industry AIML, it is the DevOps team who can really take a look at these tags and get a lot of information instead of a separate document that you kind of attach. So here what I'm just saying is I'm saying the algorithm that I have used is a decision tree classifier. This is my raw file name. This is my process file name. I have just used imputation method as a medium. I'm taking a 75 to 25 train test split. And then finally, what I'm doing is I'm logging the model or storing the entire model as an artifact, a very powerful thing that is supported by MLflow. And then there are certain artifacts like the raw file name and process file name that I also want to kind of log over here. Now let's spend some couple of minutes over here as to why, while the logging of the metrics, which is the evaluation metrics, logging of the parameters, tags makes sense. Why am I explicitly logging artifacts that I have produced? The first one over here is the raw file name, which is the file or input data that I have used to, conduct this experiment. What I'm trying to do over here is I'm asking MLflow to actually store this as a copy of the data. This is important so that when I reproduce this experiment, I use the same input data that was used at that point in time. So let's say I am conducting this experiment as of today, 31st of May. I want to pick up that input data, which was existing in the database on 31st of May. And this will become more prevalent when you are working with live connections. For example, in this case, we spoke that we are connecting to Snowflake, which is, a data warehouse. Between the time that you conducted the experiment on 31st of May, and let's say you want to share the results of this experiment somewhere around 10th of June, the table from which you kind of extracted your input data might had some more rows being loaded. And so you may want to store a local copy of the input data to ensure that when you reproduce, you look at only that data which was used to train your model. This is a very simple form wherein you are trying to ensure that the input data that you used is similar every time you reproduce the experiment. It may not be the best method, because when you're trying to store data this way, what you're doing is you are actually creating a copy of that data, and you're asking MLflow to actually store that copy of the data. For small or middle sized data sets, this is an okay method to do with. However, when you're dealing with huge data sizes, we kind of recommend using certain things like timeshare properties of the database. We also look at frameworks like data version control, which is DVC, wherein you have an entire framework of only looking at the data and not the incremental data, and all those sophisticated methods are used. However, for the purpose of this demo, to keep it simple, let's go and log a very input data, because in this case the data size is not too well. Similarly, what I'm trying to do is, once I have run all my pre-processing methods, once I have, derived my features, I'm storing that data as a process file data. Should somebody want to take a look at the actual data or the training data set that went to the model. So once I do all of this, and every time you run this experiment, all these parameters are getting calculated. And finally, I also am logging the area under curve as an artifact. Now this is actually a figure or a graph that can be stored as part of the overall artifacts to show it. Now while I'm running this, what happens is, in MLflow, under the loan predictions experiment, all the iterations that I have run are getting logged. Now, if you look at this MLflow experimentation tracking, what you see are all the experiments or all the iterations that have been run to date on this specific notebook. You can have a different notebook, a different system altogether, a different data scientist altogether working on the same experiment, and still log the outcomes to this specific experiment itself. So if you see over here, something that was run by a user called as demo day, there is another user, Ankit Srivastav, both of them probably working on the same data set, probably working on the same experiment, but logging the data to the same MLflow version. The most uh, powerful feature that experiment tracking and analysis tools allow you is to be able to compare the two experiment runs that have happened. So that is what we are trying to do over here. We are trying to see the two different results that have been achieved by two different users, and then you compare really which one is better, what is the accuracy score that you are getting, is which model or which iteration is the best iteration to go ahead with. So really a very simple and a powerful feature which allows you to compare that, hey, while when I'm just a slight change in the max depth or the parameter to the experiment, and I'm getting a different accuracy that I am kind of seeing over here. Other than that, if you look at this screen, what we are capturing is the source code. So this is the source code, or this is the Git version of the code that you have written. You have the parameters. For this particular case, it's just one. It can be many more. Anything and everything that you capture as a set parameter gets captured over here. These are the matrices that we defined and decided to capture, and these are the tags, and tags can be as many as you want to ensure that the person who's looking at this gets more visibility into the work that has been done. Now let us look at one run of this experiment that has happened. Each experiment that you run is actually getting captured as a very unique ID called as a run ID for that experiment. It is basically trying to show you what date this was run, what was the user who ran this experiment. It is showing you the source code or the path at which this is run, and then it is also showing you the git version of the file from which you can actually get the latest source code, the duration which it took, and then finally the status. There are parameters, we spoke about this. There are metrics, there are tags, we spoke about this. Let's come to something very interesting that it captured. You see over here, the process data file and the raw data file is something that is also captured and reflected over here. In addition, what I wanted to bring to your notice is that the system itself captures the config file. Now, if you take a look at the config file, what the config file is trying to say is that here are the dependencies. This is the Python version. This is the scikit-learn version. This is the Cloud Pickle thing that I have, kind of captured automatically from the source code that you have written. What this enables to do is this enables to actually then create an environment and deploy the model pickle file into that specific environment very, very easily instead of any manual work. So basically, all the artifacts, whether it is your pickle file, what is the loader module, everything that needs to be able to reproduce this experiment is actually very, very well captured in all these config files. And this is happening when you are actually doing the machine learning experiment as well. So again, to reiterate, we looked at the variables or the parameters that are uh, that impact the reproducibility, and uh, what we are able to do using an experiment tracking and analysis tools like MLflow. MLflow is just one of those tools, is to be able to capture all of these, and along with those we are also able to capture that version of the model, that version of the configuration files, which should allow us to go and deploy it into any of the other environments, ensuring that you are able to reproduce. Now, once we have this version of the model that is created, and let's say there are multiple iterations that you have done. Every time you run the Jupyter notebook, what you will get is an entry in this table, which allows you to which allows you to track all the versions, all the changes that you are doing in an automated fashion without the need of you sitting and kind of documenting it. Now, let's say one of these models is something which kind of addresses the outcomes, or is a best performing model that I believe, and I want to kind of, push it to the next environment, or I want to kind of push it, or somewhere I want to register and say that, hey, this is the baseline model before I start getting into further optimizations. Now, if I have to do this, I will, this is the latest version that I ran on 31st of May, I can go here and I can select that model and then basically do something that I called as registration of the model. This actually allows you to, tag a specific model, um, and, register it with the model registry that comes along with MLflow. Now, from an industry perspective, this becomes very, very important also, like I said, because you are looking at developing multiple models and you're looking at deploying a model across various environments. So you can have a loan prediction model version 1, which is probably something that you push to production. So it's tagged with the production environment. You can have version 2, which is, on the staging. You have done certain incremental optimizations on top of that, and you still have version 3, which is still under development. So to track all of these various models across the various environments, what we really do is we register a model. And when you register a model, it kind of registers it by its name. In this case, if I select a loan prediction model and say register, it will go and register the model with a new version. Just give me a moment while it is coming up. So here it is, the new model that we ran. It kind of shows all the details at what time this model was registered, when did you modify. Again, you can manually add certain tags over here, saying that this is a model which is XYZ and I want to, kind of tag it. And then most importantly, you can actually put a stage or tag it to one of the stage. Let's say, I want to tag it to staging. I am done with the basic development. This needs to go on to the stage. So, it will transition that specific model onto your stage environment. Now, what I wanted to really call out is that if you see this specific version of the model, we talked about traceability. This is a version 13 of the model, which is in staging. I can actually go all the way back to track all my artifacts. So from version 13 of the model, which is deployed to the staging environment, I can go back to the run ID. The run ID actually tells me the source code of the model which was deployed. It tells me what was the accuracy score. It gives me all the details, including the processed file that was used, the raw data file that was used. I can have a look at it, retrieve data from here very easily. I can look at all the other things like the imputation methods used, the train test that was used. More importantly, I can really go and have a look at the configuration file, which allows me to recreate this or reproduce this model. um, I will pause here for a second if there are any questions on the reproducibility aspects or the experimentation tracking aspects before I move forward. Okay, so let's then move forward to what I spoke about model registry. Here you will see on the left hand side a whole lot of models, registered models on this particular setup that we have. You have the latest versions of each of these models that are also kind of showing. We are talking about only three tags over here, which is the latest version, the staging, and the production, and when have we last modified. So this is something that we call as model registry. Very important when you are tackling with multiple models that are getting developed and want to track where at what stage of the development every model kind of is. Now let's kind of go back to the Jupyter notebook, which enabled us to do all of this, right? MLflow is very light in the sense that all you did to enable all of this are these 10 lines of code over here that you see highlighted. There is no restriction in terms of the tags that you can actually define. You can define multiple tags, you can define multiple parameters, you can actually define multiple matrices against which you want to kind of track. So all that you need to do to enable logging data is setting an ML flow URI and setting the experiment against which you want to start logging any experiments. This is a very powerful activity, because if you're working as a team of data scientists and you're working on your local setups without even kind of logging into a specific workspace or a specific platform, as long as you have the access to a specific MLflow server and are able to set the tracking URI and setting the experiment, you will be able to bring all your work together from different teams under the same experiment. And then as a peer or as a superior review, you can actually monitor, you can actually validate the work that is uh, happening across the team as well, trying to reproduce or trying to solve the same machine learning problem with different algorithms with different parameters, kind of parallelizing the work and picking up from the work that is happening with your co-workers as well. And I'm sure that a lot of you would be doing a lot of iterations when you are doing your research work as part of maybe the PhDs that you are pursuing, or trying to do learning path on top of one or the other existing research publication and developing something on top of it. Setting up a very simple tracking server like this is very helpful. Number one, for you to start documenting everything that you are doing as part of those experiments. Number two, this entire thing can be actually then put up as a repository and very easy for a second person who can really benefit from looking at all of this. Very beneficial from an industry perspective. Why? Because we are not only talking about the auditing that happens, but also because the time taken to reproduce a particular run is in some sense deterministic, is in some sense uh, accelerated for us when we try to take the same model and deploy it across various different environments. So that brings me back um, to how do we track reproducibility. And we I covered a very simple demo. This can get a lot complicated. As you move forward, you can actually have, like I said, tracking of multiple things right from the input data. And then for the input data here, in this case we used a very simplistic workflow of creating copy of the input data, creating copy of the uh, process data, and then taking it forward. But it can actually be very complicated setup where you're trying to actually have a version system for recording data sets, and any changes to data sets then trigger a new automated model training as well. Now, going back to doing all of this, where is it that all of this actually helps us? All of this helps us into something that we called as deployment of the model, the diagram that I kind of showed you. And let me just give me a moment to go there. Yeah. So whenever, let's say, I am happy with this specific version of my model, and I want to kind of go ahead and deploy it. How does the deployment work? How does this entire experimentation then helps me with the deployment aspects related? What we are able to do is we are able to deploy a specific version or the specific iteration of the experiment that we did using just this run id. So let me randomly go and predict any, pick up any of the run IDs saying that, hey, this is something that, is a better version of the model that I did. And it can be anything in the past. If you see right now, I'm picking up a model which is, or an iteration that was run on 30th of April. What I can do is I can, just have a very simple Jenkins wrapper, which is going to take this ID, and I run a build on top of this. Um, just give me a second. So what you see over here is a very simple Jenkins thing. We've defined a very simple Jenkins wrapper. What it allows you to do, it allows you to do pass on a run ID, which is the unique iteration that you have run, and it allows you what it is doing while it is building. If I can explain in very simple terms, is that it is going into that specific ML flow iteration. It is going and picking up this specific version of the model file, model pickle over here. It is going and reading your ML flow config file to understand where it needs to pick up the source data from, where it needs to pick up all the environment from, and then it will go and kind of deploy that specific model for you, which means that you are able to reproduce an end-to-end iteration of the work. Let's see. It is going to take some time to build, but I hope that you got the gist of where this help, this entire experimentation tracking kind of helps us uh, helps us. So here it is finished with the deployment, and it is gone and deployed it at the location that you need. So basically, kind of integrating the experiment analysis as part of your machine learning development kind of also enables the deployment aspects very easily without human involvement. So here, as if I have to go back to the point where I said, when you want to do a machine learning deployment, what you really need is you need the model pickle file, you need the environment that needs to be created on which this pickle file needs to be developed. All of this is coming as an input from the user. Vis-a-vis, when you have an experimentation tracking and analysis tool, you are enabling all of that in an automated fashion. uh, the second part that I'll come to is the features. That is not something that I plan to cover as part of this demo, but I definitely wanted to spend like 2 minutes on this topic. How do you really track all the features? Now, if you look at especially um, uh, a raw data, and then you work over it and iterate over it to define certain features, derived features. When you have actor 1 vis-a-vis actor 2, or data scientist 1 and data scientist 2 working on the same data sets, the derived features can be different. And that is what, from an industrial AI ML perspective, um, feature generations or feature versioning plays a very, very important role. So for an insurance giant, for example, you are really working on the same insurance data. You might be having a team of data scientists who are all working on the same raw data sets, and then there are certain features which are derived on top of those raw data sets. What you would want to do is an ability for those features which are worked on by one data scientist to be reused by the other data scientist or the new data scientist who are joining the teams without actually putting in the efforts to start from scratch. Okay, this is really towards accelerated machine learning model development, or at least be able to reuse and have a look at certain features which have already been defined. And that is something that we enable by a tool called as feature store. Feature stores can be built custom, so you can actually build a feature, very simple feature store on any of your existing databases, wherein you put a wrapper on top of your database, which allows data scientists to inspect all the features that have been created on a data set, and you allow them to kind of modify those. So feature store, there are a lot of feature stores. The cloud players like Amazon SageMaker, cloud players like Azure, they are coming up with feature store as part of the end-to-end ML uh, mm, development lifecycle. Uh, However, there are standalone platforms like Hopswork, which are allowing complete feature store development as a platform. Slightly advanced topic for this, but very, very important when we look at industrial AI ML, and also reproducibility, or also accelerated machine learning development, wherein you are able to create new features, version them, and then when you reproduce, you are looking at a specific version of that feature that was used to create that experiment. The third topic over there is the software environment. So Docker and containerization is what is being used. And we saw a piece of this when I just, deployed a new version of the model. What it is internally doing is it is really, really using that YAML file. And then it is going and creating a Docker image on top of that. And then that Docker image is actually used to spin up a virtualized environment and deploy your model on top of that. So in the example right now that we saw a very simple scikit-learn example, and that is why the environment that you're using is a SK environment with a pickle file. You might as well actually have somebody working on an H2O kind of an environment on the same experiment, right? And if that is happening, what it means is that when you go and deploy that, you will have to deploy it on the H2O environment, which means that you again have a conda file which defines all the dependencies. You use that to create specific Docker images and use those Docker images to go and do the deployment. uh, Hyperparameters and pre-processing units, the way to track this is through source code versioning and through tagging. uh, if you saw in the ML flow, what we did was really, we have Git integrated with it. So every time you are running experiment, it is looking at a specific version of the source code. uh, for our example, we took a very simple Jupyter notebook, which is one notebook doing everything. In actual scenario, there can be a series of Python scripts that are working together in a workflow, which means that you will have to bring in orchestration things like Airflow and Kubeflow to actually enable this. But then, from a reproducibility tracking, it's essentially, tagging all of this or versioning all of this under a source code tool, and then, putting some tags to identify and for better readability of the next user. And finally, coming to the non-deterministic outcomes, which are driven by random initialization, the way to tracking reproducibility is basically allowing for parameterized runs, which means that you allow the parameters to be set externally from the run experiments and then kind of take this requires coding changes. This requires modularization of the or the parameterization of the program which you are looking at. I am going to kind of take a pause over here at this point in time. We covered the demo, and then move on uh, to the next thing. Any questions so far? Okay. So that brings me to the last part of why we are doing this. What problems are we addressing using reproducibility? So the very first one from both research and both ML in industry that we are talking about, having a tracking server, having an experimentation tracking and monitoring tool actually allows you to enable auditing. As we saw, looking at a specific version of model in a specific environment, you are able to go back all the way towards the specific iteration. In that specific iteration, you are able to get the input data. You are able to get all the hyperparameters that were used. You are able to get all the pre-processing methods that were allowed, and finally look at the actual source code as well. All of this is very easily enabled without missing out on something. So that is one of the key aspects that are addressed when you try to use a reproducibility and you use experimentation tracking and analysis or monitoring tools as part of your machine learning development. We saw it removes person dependencies. It tracks it as you kind of conduct the experimentation using your Jupyter notebooks. And that way most of the tracking tools including ML flow are very extensible, in the sense it's not necessary for you to just use sklearn. They have multiple modules including deployment to Amazon SageMaker, also H2O specific modules. All of it can be used whichever environment you are using to kind of start tracking your results into the MLflow tracking server. Allows for faster implementation. This especially becomes important from an industry IML perspective, because everything that we run is run in the time bounds as a project. So you're looking at making a machine learning AI enabled application against a specific timelines, while the first draft model that comes typically goes into iterative mode. Once you have done the first draft, the time going into reproducing that, the time going into deploying that across various environments has to be reduced. And we saw that how once you have defined and kind of finalized the specific version of the model, you can really use these capabilities to start deploying the model across various different environments by enabling model registry and so on and so forth. Of course tracking for peer and superior reviews. I didn't go into a lot of details of catching all the outcomes as part of graphs and visualizations, which you can also do as part of ML flow, and kind of use that as a supervisory or a review kind of an effort, where they can really see the outcomes associated with a specific experiment, and they can run the experiment actually completely independent without you being there to see the results. Optimization certainly, and then of course all of this kind of translates into costs for us when you are reducing the time and the effort for faster implementation with removing the person dependency. So with that, I am kind of at the end of my talk. I'll be happy to take any questions that we have at this point in time.
I think, thank you. I think very, Sham here. I think a very relevant and useful. Just a quick question. Have you seen this um, well deployed in many organizations? In particular, I'm actually more interested in government and, those kind of public sector kind of places. Have you seen this kind of framework being used?
Uh, my my exposure to government work is limited, Dr. Sham, so I will not answer that. But in an industry, yes, this is something that we are seeing across. Inherent need comes from the fact that for a long time machine learning was always treated as a uh, the development aspects were always treated more researchy, and in that sense not necessarily falling into the standard computer science development paradigm. So CI/CD for machine learning is something that has been that started coming in only in the last year or so. And the increased need has come from a point where the industry has started really adopting machine learning and AI in the mainstream. Till some point in time, it was more of POCs, research, or okay, not really coming into the mainstream applications. Now that it is happening in that way, the increased need for having such frameworks to be able to track all the work that is happening becomes inherent and important. I i having said that, I do not see why this adoption should not be happening in public sector, why this adoption should not be happening in government, because there the need for governance, there the need for auditing, there the need for being very very sure of what model is going into the production, comparison of various models that are happening becomes of paramount interest, right? In an industry, at least we are looking at one team of data scientists who's working on solving a specific problem. When you work at a public sector, it's actually a whole more community which is kind of contributing. So enabling such platforms where under a hood of a experiment you have multiple people contributing, and they getting a chance to actually see other people's work and see what are the parameters they are working, or even compare their work with the existing baseline works, becomes of paramount important in my opinion.
I agree with you. I was just more curious to see whether in your research you had found that, because I don't see too much of that being published. So I was just curious whether you had in say, any specific insights. See, private organizations and private enterprises, I agree, adoption has been well taken up. But I've not seen any mainstream use case. Maybe I've not seen enough. So I was thinking whether you had any um, vision on that, but that's fine. Thank you for the answer. But
No,
good session.
unfortunately, no. My work and my entire research has been more towards operationalization in the industry aspects more than anything.
Hello, am I
Yeah,
audible?
hello, Akash here. So on chat, I have asked a question regarding TensorBoard versus ML flow from research perspective regarding graphs and visualizations. But I think you have answered that question towards the end of your presentation.
Okay. So thank you so much, Anibha. It was a wonderful session, especially, you showed the browser and how the ML flow works and so on. So it was very helpful to understand the particular concept. And now we are towards the end, of this particular course that we had in collaboration with Persistent Systems. And we'll be having a short valedictory sort of remarks. And for that, we have with us from Persistent Systems, we have with us Dr. Pandurang Kamath. So Dr. Pandurang Kamath is the Chief Technology Officer at Persistent, and he helps enterprise unlock business values through technology and innovation. So can we, uh, yeah, over to you, Dr.
Yeah,
Pandurang.
sure. Thank you for having me. I have had a bit of trouble with my webcam, so that's why I haven't been able to turn it on. Sorry about that. First of all, I hope all of the students who have been taking this course, I hope you have not only enjoyed it, learned something practical and actionable from it. We are very proud to be associated with the PKC Pune effort in driving this important initiative. AI and digital world is actually more and more part of our life, and over this coming decade, AI will play an important role in the way we interact with the rest of the world, the way our government and us interact as well, and the services that are delivered to us. So we felt that an important part of this is to ensure that the systems we build are responsible. And towards that, I am really, really proud of my colleagues and the PKC team that have stitched together this incredible range of topics that you have learned over the last 9 weeks or so. And we have tried to cover in this everything from what responsible AI really means, how to check for bias, how to make AI more explainable, how to ensure that we are able to deliver experiences and services in an equitable, fair manner to those who experience the systems we build. So I hope you take this thing forward, and even when you're building, whether it's in your educational projects or job later on, you not only keep this in mind, but spread this word and that these are important facets of system building and practice them. We are more than happy to engage with you further, and if you ever decide to work for us, we'll be more than happy. We have a wonderful data and AI practice that Anibha is a leader at, so we'd be happy to talk to you on that front as well. I'll keep it short and sweet. With that, thank you very much. Back to you, Prachi.
Thank you so much, Dr. Kamath, for your remarks.
Prachi, your audio. Yeah. Okay. Can you try again? Audio was low
Yes.
again.
So, is it okay now?
Yes.
Yeah. So thank you so much, Dr. Kamath, for your remarks. And we also have with us Professor Kembhavi. Professor Ajit Kembhavi is the principal investigator of this Pune Knowledge Cluster. He is an astrophysicist and ex-director of Ayuka Pune. So over to you, sir.
Thank you very much, Prachi. So I'm addressing both the lecturers as well as the participants. It has been wonderful to have this course by Persistent Systems. Now, Persistent Systems and I personally go back many, many years. Through Ayuka, I've been collaborating with Anand Deshpande and his team for well over 20 years. And in the beginning, it used to be data-related things, and now we are getting into AI-related things. So part of the mission of the Pune Knowledge Cluster is to have high quality capacity building courses. And we have been very fortunate in getting some of the best people in the city and even best people nationally to deliver these courses. We had several courses in biology, and then we have had two courses in IT. One was NLP by ICETIS and this course on responsible AI by Persistent Systems. Now, I myself work in AI, applying AI to astronomy and biology and other domains. And I regret very much the fact that I could not attend this course because of shortage of time. Once in a way, I used to plug in and listen to things for just a few minutes, but I couldn't do anything more than that. The point is that uh, AI now has become pretty commonplace. And I find that even young project students, people from second year engineering onwards who work with me, uh, they're pretty proficient in running AI codes, and they have got a fairly good basic understanding of AI. And it will not a really difficult matter to just keep developing the technical understanding. And it's not easy, but it is not impossible, and many people do it. But I feel that what is required now is to get a deeper insight into the domain and what effect it has on everybody and what are the underlying issues which will become very, very important in the future. And I believe that courses like Responsible AI go very far in doing such a thing. I kept tab of what was going on, and I find that the lectures were very well received, and the people who attended them seemed to be engaged, and then there'll be an interactivity. And Prachi told me just a little while ago there's also going to be an extra interactive session, the 10th lecture. I think that that's all that is an extremely welcome development. And it is not easy to give these courses because people have to take time off from their activity to focus on it and to engage with students. And I've forgotten who it is, but I know that one lecturer uh, was down with COVID and Prachi was persuading him to not talk, but he did. Okay, so that is the kind of dedication uh, that we are used to from Persistent. And the PKC has benefited tremendously by this interaction, and we hope to take it much further in the future. So I thank the participants for the diligence that they have shown in learning from the course, and I thank Persistent Systems from the bottom of my heart for how much they have done to make this course a success. Thank you.